Okay, these are nothing but the shapes of d orbitals. So x square minus y square is concentrated on x and y axis. Dz square is concentrated on z axis, and dxy is concentrated in between x and y axis. And here we can see that dyz is concentrated in between y and z axis. Okay, is concentrated in between y and z axis. Whereas dxz, we can see here that it is concentrated along xz. Okay, so this is x axis and this is z axis, and it is concentrated along the x and z axis. Okay, so these are the d orbitals. This is Eg orbital. This is nothing but in between the axis is nothing but T2G orbitals, and these are nothing but Eg orbitals. Okay. Now here we are able to see the approach of the ligands. This is the central metal ion. What we మనము ఏదైతే మనము చెప్పుకుంటున్నామో central metal ion is nothing but is the central metal ion. Okay, negative electric field around the negative electric field around the central metal ion is nothing but these are the negative electric field around the central metal ion. Okay, so this shape is like ఏంటంటే pyramid shape అన్నమాట ఇది. ఓకే, అప్పు ఒక పిరమిడ్ ఉన్నది, కింద ఇంకొక పిరమిడ్ షేప్ లో ఉన్నది అనమాట. అట్లా అప్రోచ్ అవుతున్నాయి అన్నమాట లిగాండ్స్. సో క్రిస్టల్ ఫీల్ ఆక్టాహైడ్రల్ కాంప్లెక్స్. ఓకే, ఈ అప్ పిరమిడ్ డౌన్ పిరమిడ్ ఉన్నది ఏంటంటే ఇది ఒక ఆక్టాహైడ్రల్. ఈ షేప్ ని ఆక్టాహైడ్రల్ అంటారు. సో ఇక్కడ సెంట్రల్ మెటల్ అయాన్ ఉంది. ఆ మెటల్ అయాన్ చుట్టూ ఏంటంటే మనకి లిగాండ్స్ దగ్గరకు వచ్చేస్తున్నాయి అన్నమాట. లిగాండ్స్ ఓకే, ఆక్టాహైడ్రల్ ఫామ్ లో లిగాండ్స్ అనేది దగ్గరకు వస్తున్నాయి సెంట్రల్ మెటల్ అయాన్ దగ్గరికి. ఓకే, సో ఈ డయాగ్రామ్ అనేది ఇక్కడ మనం చూస్తే ఇగో ఇదేమో dz స్క్వేర్, ఇదేమో dx స్క్వేర్ మైనస్ y స్క్వేర్ ఆర్బిటల్ కాన్సంట్రేటెడ్ ఆన్ ది యాక్సిస్. నౌ ఇక్కడ చూస్తే xy ఇదేంటంటే xy is concentrated in between the axis. dxy is concentrated in between the axis. Okay, dyz is concentrated in between y and z axis. dxz is concentrated in between x and z axis. Okay, so ఇట్లా చూసుకుంటే ఏంటంటే ఏదైతే యాక్సిస్ పైన ఉన్నాయో అవి ఎనర్జీ ఇంక్రీజ్ అవుతాయి అన్నమాట. ఏదైతే ఇన్ బిట్వీన్ యాక్సిస్ ఉన్నాయో అది ఎనర్జీ డిక్రీజ్ అవుతుంది. ఓకేనమ్మా. So we will go to the next slide. So whichever is there present on the axis, there will be increase in energy. Whichever is present in between the axis, there is reduction in energy. So how energy is reduced for the orbitals that are present on the axis, and how energy is increased for the orbitals that are present on the axis, and how energy is reduced for the orbitals that are present in between the axis, we will study here. Okay. So ఏంటంటే ఇక్కడ ఈ పాయింట్ ఫస్ట్ పాయింట్, ఇఫ్ వి సీ దిస్ ఫస్ట్ పాయింట్, ఇక్కడ మనం ఫస్ట్ పాయింట్ చూసుకుంటే సెంట్రల్ మెటల్ అయాన్ is surrounded by 6 ligands as shown in the figure. The central metal ion is surrounded by 6 ligands as shown in the figure. Okay, previous figure. Now ఏంటంటే when central metal ion is surrounded by 6 ligands in an octahedral complex, ఏంటంటే what will happen is the electrons of the ligands, the electrons of the ligands will have some kind of have attraction with the positive charge of the metal ion. Okay, metal ion is positively charged and ligands are negatively charged. So because of positive and negative, there is attraction in between the metal ion and the ligand. That is nothing but attraction. That is nothing but attraction. Now repulsion is nothing but so here we are able to see the d orbitals, how ligands are approaching the metal ion. So this is ligands are negatively charged and metal ion is positively charged. So there is an attraction between the positive charge of metal ion and the negatively charged ligand. Okay, that is nothing but attraction. And when ligands are approaching the metal ion in an octahedral fashion, the metal ion have the electrons that are filled up in the d orbitals. Okay, so the electrons of the metal ions that are filled up in the d orbitals have a repulsion with the electrons of the ligand ions, have a repulsion along the ligands of the ligands. The electrons that are filled up in the metal ion have repulsion towards the electrons of the ligands. Okay, now let us go to the next slide here. So here attraction is nothing but there is an attraction between positive metal ion and the negative ligand. That is nothing but attraction. Repulsion is nothing but there is a repulsion. There is a repulsion between the electrons of the metal ion and the electrons of the ligands. Okay, there is a repulsion. There is a repulsion. Now here in this slide, we can see that we know the lobes of dx square minus y square and dz square orbitals point along x, y, and z axis where the lone pair of electrons approach. Thus, the electron residing in this orbital will experience a greater repulsion. So the energy of dx square minus y square and dz square orbitals are increased. Okay, so this dx square minus y square dz square orbitals, they are present on the axis. Okay, they are directly influenced by the ligand. So that's why their energy is increased. Whereas dxy, dyz, and dzx t to g orbitals, these are t to g orbitals, they are present in between axis. They are present in between axis and they are not present on the axis where the ligands are approaching, and that's why they have minimal repulsions with the ligands and their energy is reduced. Okay, that's why their energy is reduced. Okay, let us go to the next slide. So here we are able to see, okay, this is the metal ion. Metal ion is positively charged, ligands are negatively charged. Metal ion and ligand, positive and negative, there is an attraction. Okay, that is electrostatic attraction, positive and negative. We know that positive and negative will attract each other. So that is the reason why bond is forming between metal and ligand. But problem is now metal has electrons present in them. Now ligand has electrons. So the negatively charged electrons in metal and negatively charged electrons of ligand have some kind of repulsions. Because of these repulsions, there is increase in energy of some orbitals and there is decrease in energy of some other orbitals. Okay, so attraction is that nothing but positive metal ion and negative ligand attraction. Negative electrons of metal ion and negative electrons of ligand have repulsion. Okay, attraction and repulsion. Now repulsion, which will have more repulsion and which will have less repulsion, we have to see. Here, whichever orbitals are present directly on the approach of the ligands have more repulsion. Whichever orbitals that are present in between the axis, in between the approach of the ligands, they have less repulsion. Okay, here we can see that these orbitals, these are the orbitals that are present on the axis dx square minus y square. They are influenced more by the ligand. Here dz square is present directly on the approach of the ligand, so influenced more by the ligand. Here dxy is present in between the x and y axis and they are not influenced by the ligand. Here dxz is present in between the axis, they are not much influenced by the ligand. Here dyz, they are present in between the axis, they are not much influenced by the ligand. Okay, so these two are influenced. These are more influenced. These are less influenced. Less repulsion, more repulsion. More repulsion, less repulsion. Directly on the axis of the ligands, more repulsion. In between the axis of the ligands, so they are less repulsion. So in this slide, we can see that metal ion and ligands are attracting. Metal ion or ligands are oppositely charged. Okay, that's why there is an attraction. Now electrons of this dz square and dx square minus y square, there is repulsion. Okay, directly on the axis, whatever orbitals are present, they are repulsion. Okay, in between the axis, whatever present, they are decreasing in energy. Less repulsion. Okay, less repulsion, more repulsion, increase in energy, less repulsion, reduction in energy. Okay. So these are T2G set of orbitals. These are EG set of orbitals. On the axis EG set, in between the axis T2G set. Okay, on the axis EG, in between T2G. On the axis EG, in between T2G. T2G is reducing and EG increasing in energy. Here, read this. D orbitals pointing directly at the axis are affected most by the electrostatic interaction. Therefore, they are increasing in energy. D orbitals not pointing directly at the axis are least affected by electrostatic interaction. That's why they are reducing in energy. So in this slide, we can see metal ion is there. This is the metal ion, central metal ion, and ligands are approaching. Okay, so ligands are slowly approaching. When ligands are approaching, there is an increase in energy. And when ligands are approaching circularly, there is increasing in energy. When ligands are forming this octahedral complex, one pyramid above and one pyramid below, then they are splitting. Okay, orbitals are splitting into T2G orbitals and EG orbitals. EG orbitals are present on the axis, okay, directly on the approach of the ligand, increase in energy. They are present T2G orbitals in between the axis. That's why they are reducing in energy. So here we are seeing there is a overall reduction in energy because of the electrostatic interaction of positive metal ion and negative ligand. Okay, here we are seeing the d orbitals dx square minus y square on the axis, dz square on z axis, and dxy in between x and y axis, dxz in between x and z axis, dyz in between y and z axis. So now here we are seeing that seeing the metal ion is there, metal cation increasing in energy, and metal cation increasing in energy, and octahedral complex is forming, and there is a splitting up of d orbitals into T2G and EG orbitals. T2G orbitals and EG orbitals. Okay, in this slide, we are able to see the crystal field splitting of FeCN6 complex, an octahedral complex. Crystal field splitting of FeCN6 3 minus, an example of octahedral complex. So here we are seeing that FeCN6 3 minus. This is an example of octahedral complex. Now 6 CN ligands are approaching the iron. Okay, 6 CN ligands. 6 CN ligands means each CN is carrying -1 charge. So 6 CN ligands means -6 charge. X minus 6 is equal to total charge on the complex is -3. Okay, x minus 6 is equal to -3. So x is equal to -3. When -6 comes here, it becomes +6, and it is nothing but +3. X is equal to +3. Means iron in FeCN6 3 minus complex has +3 charge. Iron in FeCN6 3 minus has +3 charge. So FeCN6 3 minus is an example of octahedral complex. FeCN6 3 minus is an example of octahedral complex. Fe3 plus has 3d5 electronic configuration. Octahedral complex. Fe3 plus has 3d5 electronic configuration. Very important. Fe3 plus is having 3d5 electronic configuration is very, very important for us. Okay, 3d5 electronic configuration. Okay, let us see how atomic number of Fe iron is 26, and this is nothing but the electronic configuration of iron. Okay, with atomic number 26, 3d is having 6 electrons and 4 is 2 electrons, 4p is 0 electrons, and Fe3 plus means 3 electrons are going from this Fe, and it is being becoming Fe3 plus. When 3 electrons are going from Fe, here 2 electrons are going, here 1 electron is going, and so total Fe3 plus is these are the total number of Fe3 plus electrons that are present. Now Fe3 plus in FeCN6 3 minus. Fe3 plus in FeCN6 3 minus is nothing but 2 electrons, 1 electron. We can see here that crystal field splitting of octahedral FeCN6 3 minus. Initially, the ligands are approaching. When ligands are approaching, all are increasing in energy. When it is forming octahedral complex, the T2G orbitals are coming down and EG orbitals are going up, and this all electrons are getting filled up in the T2G orbitals. Because all electrons are getting filled up in T2G orbitals, because this splitting energy is more. This splitting energy is more. That's why all electrons are filled up in T2G orbitals. So here, if we see that there is one unpaired electron, we are able to see here that there is one unpaired electron. Since the complex has one unpaired electron in the T2G orbital, this complex is paramagnetic. Okay, since there is one unpaired electron, the complex has one unpaired electron in the T2G orbital, and that's why this complex is paramagnetic in nature. Okay, so FeCN6 3 minus is the complex, octahedral complex, example, octahedral complex, and Fe has a +3 charge. Fe has +3 charge, and atomic number of iron is 3d6 and 4s2, 4p0, and Fe3 plus means 3 electrons are going out from iron, 2 electrons are going from 4s, and 1 electron is going from 3d. So total number of electrons that are going are like this here. Now Cn minus is getting paired up like this, and since there is one unpaired electron, the magnetic property, this is paramagnetic in nature. This is paramagnetic in nature. Okay, filling up of electrons in d orbitals. Filling up of electrons in d orbitals. Arrangement of electrons in octahedral complexes. How electrons are arranged in octahedral complexes. Okay, there are two kinds of ligands: strong field ligand and weak field ligands. Strong field and there are two kinds of ligands: strong field ligands and weak field ligands. Strong field ligands. Strong field ligands. Strong field ligands and weak field ligands. Strong field ligands are like this. Weak field ligands are like this. Strong field ligand electrons are distributed in this way. Weak field ligands electrons are distributed in this way. Okay, in case of strong field ligands, the electrons are paired up, okay, in T2G orbitals, whereas in weak field ligands, the electrons are going to EG set. Okay, T2G and EG set, two orbitals are there. If energy difference between these two orbitals is energy difference between these two orbitals, if it is more, then electrons will remain here only. If energy difference is less, then electrons are go up. Electrons will go up. Here, one electron, second electron, third electron, fourth electron, instead of going to, it cannot go to EG set because EG set is very far. So that's why it will remain in T2G. Okay, D5, D5. So D1, 1 electron, D2, 2 electrons, D3, 3 electrons, and D4, fourth electron will not go to EG set, it will go to T2G. Fifth electron will not go to EG, it will remain in T2G. Sixth electron will remain here only. Okay, seventh electron, now all are filled up, seventh electron will go to EG. Okay, now eighth electron, here now eighth electron is there, eighth electron will go to EG set here, it will come to EG set. Now ninth electron is the ninth electron will pair up here, and 10th electron will again pair up here. Okay, D1 electron is 1 electron here, D2 is 2, D3 is 3 like this, D4, fourth electron, no EG, it will go to T2G. D5, no, it will not go to EG because very far, high energy, and it will be remaining in T2G. D6 here only, and D7, all are filled up, it will go to EG. D8, all are filled up here, it will go to another EG. Then pair up here. Okay, if you see the number of unpaired electrons, one unpaired electron is there. Okay, here what I have written is wrong here actually, I'm sorry. Here I have written wrong. Now here we see one unpaired electron is there, two unpaired electrons are there, three unpaired electrons are there, then two unpaired electrons, one unpaired electron. Here unpaired electrons are 0, all are paired up. Here unpaired electron 1, here unpaired electrons are 2, here unpaired electron are 1, here all are paired up. Okay, so wherever unpaired electrons are there, they are paramagnetic. Wherever there is paired electron, it is diamagnetic. This is in case of strong field ligands. Now, when we go to weak field ligand, T2 energy difference between T2G and EG is very less. Energy difference between T2G and EG is very, very less. Okay, so now, when energy difference between EG and T2G is very, very less, one electron, D1, one electron is here, D2, two electrons are here, D3, three electrons are like here, filled up like this, D4, fourth electron, here it filled up here only, but in here, D4, electron is going to EG set. Okay, D4 electron is going to EG, top it is going. Here D4 electron is remaining down, whereas here D4 electron is going top. D5 electron is going top here. Here D5 electron is remaining down. Okay, D6 electron is again after filled up here, it will come here down. Then D7 electron again here it will be another electron. D8 another electron here. D9 another electron here. D10 another electron here. So if you see the number of electrons again, D1 one electron is like this, D2, 2 electrons, D3, 3 electrons, D4, 4 electron, fourth electron is going top. Here, fourth electron down because very far energy. Here, very less energy, that's why going to EG. D5 electron is going here. D6 electron is remaining down. D7 electron remaining down. D8 electron down. So down filled up, now going up. D9 electron going up. D10 electron going up. Okay, so number of unpaired electrons, if you see here, D1, 1 unpaired electron, D2, 2 unpaired electrons, D3, 3 unpaired electrons, D4, 4 unpaired electrons, D5, 5 unpaired electrons, D6, 4 unpaired electrons, D7, 3 unpaired electrons, D8, 2 unpaired electrons, D9, 1 unpaired electron, D10, 0 unpaired electron. Okay, so unpaired electrons means paramagnetic, no unpaired electron diamagnetic. So here we can see that whatever is present, increasing order of ligand field. Okay, here it is weak field, here it is strong field. Okay, strong field is there, electron distribution is like this. Okay, so electron distribution is like this, strong field. When it is weak field, the electron distribution is like this. In case of weak field, strong field, electron distribution is like this. Weak field, electron distribution is like this. So here is a strong field. This is a strong field. This is a weak field. Okay, strong field, electrons are down. Electrons are down. Weak field, here this is a strong field, this is weak field. D4, strong field, weak field. Strong field down, weak field up. Electron is going up. Electron is remaining down here, made up. Whereas in case of weak field, electron is going up. So D5, this is strong field, this is weak field. Strong field, energy is more, and that's why electron is remaining down. Here D5, this is a weak field, electron is going up because energy is very less. D6, electron is remaining down. Here D6, electron is going up. Electron is actually coming here. Here, after filling up here, electron is coming here. Okay, very important. D7, electron is going here. After completing filled up here, electron is going up here. Okay, like that. So here we can see this this is far, means this energy difference is far. That's why they are remaining down. Whereas this energy difference is less. That's why electrons are going up. This difference is small. This difference is large. That's why they are down. Large difference down. Small difference going up. Now here unpaired electrons are there, paramagnetic. Here unpaired electrons are not there. That's why this is diamagnetic in nature. This is FeCN6, strong field. This is FeH2O6. This is a weak field ligand. Strong field ligand, more energy, electrons are down. Weak field ligand, energy difference is less. That's why electrons are going up, and this is paramagnetic in nature. Let us go to the next slide. Okay, till now we have studied the crystal field splitting of octahedral complexes. Okay, So this is nothing but octahedral complex, central metal ion. Ligand is in the form of octahedral. Ligands are approaching the central metal ion in the form of octahedral. Okay. So whichever orbitals, d orbitals that are present on the axis, they will undergo more repulsion, and therefore there is an increase in energy. And whichever orbitals that are present in between the axis, they have lesser repulsions, and that's why they are reducing in energy. Okay, these are the orbitals dxy, dyz, and dzxz. These are the orbitals that are present in between the axis, and that's why there is reduction in energy for these orbitals. These are the orbitals that are present directly on the axis, directly on the approach of the ligand. That's why there is increase in energy. So the two kinds of interactions that are seen are attraction and repulsion. Attraction is nothing but positive metal ion and the negative ligands are attraction. That is attraction. Whereas the electrons of metal ion and the electrons of ligands have repulsion. Okay. Now the repulsion of orbitals, the repulsion of orbitals that are present on the axis or more, that's why they are increasing in energy, whereas the repulsion of the dxy, dxz, and dyz orbitals are less, that's why they are reducing in energy. Okay, so these are EG set of orbitals, they are increasing in energy, whereas these are T2G set of orbitals, they are reducing in energy. Okay, here we are able to see that these are T2G set of orbitals which are reducing in energy. These are EG set of orbitals that are increasing in energy. Okay, they have raised up, increased in energy. These have lowered down, they have reduced in energy. So here we are clearly seeing initially when the ligands are approaching, there is increase in energy, and when the ligands are forming octahedral complex later, there is a reduction in energy for T2G orbitals, and there is increase in energy for EG set of orbitals. Because EG set of orbitals are present on the axis, that's why there is increasing energy, whereas T2G set of orbitals are present in between the axis, that's why they are reducing in energy. This is an example. FeCN6 minus 3 minus is an example of octahedral complex, and this is how the electrons are distributed in the octahedral complex. And since there is one unpaired electron, and the complex has a magnetic nature, and that's why it is called as paramagnetic molecule, paramagnetic complex. So this is what we have learned in our today's class: crystal field theory, octahedral complex, how splitting is occurring in octahedral complex, how T2G orbitals are reducing in energy, and how EG orbitals are increasing in energy, and how electrons are distributed in case of